So what I'd like to do is go a little bit into chapter one and lecture on some of the more important material. Chapter one is actually a relatively short chapter, and it really only has um, one or two important things in it. Okay, so that's all I'm going to cover. It does not mean I won't test you on a few of the other things that might be in the chapter, but for sure, the things I cover in lecture will be. So what this means is, as I lecture, I'll be covering topics, some of which you may have to go back into your textbook and actually look at more closely and understand it that way rather than relying on my lecture. So I try to hit the spots that are the most difficult. I kind of go through fairly quickly the stuff I think is maybe not as difficult. And I try to cover all the stuff that's going to be potentially on the test. There are also practice exams. They're not really practice exams, but they're like study guides for the chapter. So if you're curious, like, gosh, what is Dr. K going to cover in this chapter? You can look at those practice tests or the study tests to see, like, the type of topical material that I'm going over. Okay. Now, just so you know, I'm going to upload this file, and when you see the first page, it's actually going to look like this. And this is really a note to the students, the audience that I'm writing it to. I've stripped a lot of the language out of it. That is the wording that's in here, because I'm going to talk through it and have you guys fill it out. And every year, kind of, it's a little different, anyways. And I update these basically every time I teach the class. What this stuff up here says is I'm basically teaching this class because I like this class. I don't need to teach this class. It's not part of the classes I'm asked to teach, but they need someone to teach it, and so I like teaching it. All right, so before we get started, let's talk about what chemistry is. Okay, so chemistry is the study of matter, right? And what it does. So that's a part of the statement that's missing up here. And what it does. So here's the thing. Um, what's matter, right? Matter is, they say anyways, has mass and occupies space, right? For objects like my cell phone or my friend the cantaloupe, right? Um, those things are obvious. You can put your hands on it, it's matter. But it also turns out things like air, because air turns out to be has a mass, and we don't think about it, but the air around you has weight. Like, you could actually weigh the mass of air. And it also takes up space, and so those are the qualifications for matter: is space and mass. Okay, so, and chemistry studies what those things do. So when we talk about chemistry, it covers lots of stuff that overlaps with other areas of science, like physics or biology, it's geology, a lot of different fields. It's considered to be, in the name of chemistry for many years, or the title of chemistry, has been the central science, because it sort of ties a lot of stuff in together. I studied what's called analytical chemistry and got my doctorate a long time ago. And my sons, two of my sons right now, my older two, are getting PhDs in agricultural chemistry. So that's a whole different area of chemistry than what I studied. But again, they studied agriculture, I studied neuroscience, but these are all considered branches of chemistry, right? So, anyways, just thought I'd throw that out there. Now, the scientific method, it's the way we try to look at the world objectively, okay? And I'll write this out in a second. It's the way we try to look at the world objectively to understand what's going on around us, okay? So we look at a way of looking at the world, objectively, to understand what's going on around us. Now, I could have easily have typed that. When I write it out like this, because I feel like if you follow along and you write it out, you have a better chance of remembering it. So I'll encourage you to print out the blank versions of these notes and write along with it. I'll even post the written versions, but I encourage you to just sort of write along with it if you have the time. There's going to be days, I know this is the 4-week summer session, you're just not going to have time, okay? So the scientific method begins with observation, okay? Observation is just looking at the world around us. My friend, the cantaloupe, this has become the prop for the summer. I promise I won't keep it past like today. I don't know if you can see these spots on it, right? There's spots on my cantaloupe. I think it's probably rotten. So this is my observation. There are unusual spots on my cantaloupe, right? Observation is literally that. It's what you see. So it's data. It says what you see or record. And then the question is, what does that mean about my cantaloupe, right? Well, it could mean a lot of different things, but my hypothesis, right, is what I think it means. So hypothesis is a statement about what the observations mean. But, for my cantaloupe, I'm thinking it's rotten. What I think my observations. Sorry, that's really sloppy handwriting. It's actually the second time I recorded this because the mic was off the first time. So anyways, all these things I say, I probably shouldn't. Okay, so it's what I think it means. And so in this case, I'm wondering if my cantaloupe is rotten, right? So here's the thing. Hypotheses, that's plural of hypothesis. Hypotheses are testable. Right? So if it's testable, the test is what we call an experiment. So this is the test of the hypothesis. So here's the thing, okay? The test that I'm going to come up with later is a destructive test. I'm going to cut it open. After that, it kind of answers the question. But a lot of things in science are little black boxes, and we don't really know, or we don't quite understand. And so we have to test it and see how the data comes out, okay? But this is what's going to happen. In my experiment, if it was not destructive, I can go up here, and I could reformulate my hypothesis depending on how the data came out. Now, we like to think of things as being black and white or clear cut. Maybe that's a better way to say it. Clear cut. Like it's either this way or that way. But in science, right, just like a piece of fruit, it's not always that way. So when I grew up, I worked in packing sheds, and I worked to cull fruit. So to explain what that means, in case you don't know what it means, packing sheds see a lot of fruit. They go along a conveyor belt, at least the old ones. And then what you would do is you would learn to recognize what a bad piece of fruit looked and felt like. So you'd actually put your hands on all the fruit. And then when you found a cull was a bad one, you'd throw it out. That's what they mean by culling it. Okay, so anyways, for a piece of fruit and a person doing it, that is a pretty clear-cut situation where you're kind of going through. But now let's say you have a packing shed, not the size of the one I grew up in, but maybe like one of the larger ones in town here where they're seeing 1 million pieces of fruit a day, right? You don't rely on individuals necessarily to do that. And so what you do is it becomes a grace kind of thing. You have to figure out how to figure out whether or not a piece of fruit is bad. And so you come up with a hypothesis like this fruit will be, I can tell this fruit is bad if its density is such and such, or if it sinks in this type of solution. If it sinks in this type of solution, we'll assume it's bad and we'll throw it out. That kind of thing. And then what you do is you get like 1 million pieces of fruit, and you have people go through by hand and sort them out, and you have a machine do the exact same thing, and you try to tell whether or not they pick out the same thing or not. Okay, So you have to come up with a hypothesis and do an experiment, and you run your experiment, and then you check to see your data, right? The experiment, the feedback, the test of the hypothesis, this feedback is your data and results. Now, data is just another word for observations, right? And so we're going to take new observations, feed it back into our hypothesis. Eventually, you might come up with a theory or you might come up with a law. Now, a theory, just to make this real clear, is not the same as a law. And the big distinction is a theory tries to give the underlying explanation about the way things are. Okay, theory tries to give I can't spell lying reason why things are the way they are. Now, these are not textbook explanations or definitions, right? But these are like the way I think about them. If you really want the textbook's definitions, let's go in the back of the book and you could read the glossary. But you could have done that without this lecture, so I'm trying to give you more like context, right? A law just tells you what the relationship is. Okay, so it gives the relationship between the observation, right, in the experiment and what happens. It tries to explain the relationship between what goes in and what comes out. Okay, so how are those statements different, right? A law doesn't try to explain it. A theory tries to explain it, right? So just give you some examples of how laws might be, or theories might be written that's different from the way laws are written, okay? So this is one of these is a theory that's John Dalton's atomic theory, and one of these is the law of conservation of mass, which was sort of developed by a guy named Anton Lavoisier. So read Dalton's atomic theory, right? All matter is composed of atoms. All atoms of a given element are the same. This is some of the postulates, right? Some of the ideas. Compounds are combinations of two or more different elements. Now that's a testable idea that has an underlying reason why, right? Underlying reason for why atom or molecule compounds are different from each other, but they're just composed of different kinds of elements. And then chemical reactions are just rearrangements of atoms. So you could take two substances. For example, if you take hydrogen and oxygen, and you combine them together, like make a balloon. I'll make a balloon. That's like a cloud. Here, I'll make a balloon. This is a balloon. And you put hydrogen in here, and you put oxygen here, and you light it on fire. It will explode very loudly, trust me. It's not something you really want to do without any help. And you're going to get water out of it. So, right, water is just composed of these two elements, oxygen and hydrogen. Now, you may be familiar with atoms as O and hydrogen, right? Atoms of hydrogen, but the elements oxygen and hydrogen are O2 and H2, and we'll talk about that more later. But this is an explanation of compounds and an explanation of elements, right? Now, here's an example of a law, and there's actually two of them here. I'm just going to talk about conservation of mass, but imagine you had a rock. And I'm going to draw it like this, actually. There's my rock. It's not a very good looking rock. And I broke it into two halves. Like that, okay? If I measured this mass, put it on my scale, and call that mass 1, call this mass 2 and this mass 3. So I go through and I measure it, right? If I take M2 and M3 and I add them together, what's it going to equal? Well, most of you probably thought, well, it's probably going to be M1, right? Do you know why that is? There's no explanation, right? It's the conservation of mass. And the thing about a conservation is it says mass is conserved, and chemical and physical processes just means that what you started with is what you end with. Okay, so it doesn't provide any explanation of why it's that way. Now that one to us physically is a little easier to understand. But when we talk about energy, it turns out the same is true of energy. So if the amount of energy you start with in any process has to be the same as the energy you end up with. Now, the energy is rearranged because the molecules and atoms are rearranged, right? But there's no explanation for that in the law of conservation of energy. It just says what you start with is what you end with. Another famous law is Einstein's law. Right? That equation doesn't actually provide a reason why energy is equal to the mass times the speed of light squared. Now, in his theory, he talks about why that is, but the law, Einstein's equation is a law, right? Doesn't provide any explanation. So this is what we're going to do. Oh, yeah, here's another one. This is kind of a fun one because I figure there's a lot of biology types in here. Or people in health or whatever. There's this thing called Kleiber's law. It's been around for a long time, and it's the heat generated by an animal is always proportional to its mass to the 2/3 power, right? Now, it turns out there are exceptions to this, but when Kleiber came up with this idea a long time ago, I don't think he knew about a lot of exceptions. And here's the mass, right, of a whale, or the energy of a whale plotted versus the mass of the whale, right? And here's the energy of a mouse. And they fall pretty much on the same line. Everything in between. There's rabbits, there's dogs. Like he didn't have a lot of exotic things. He had an elephant in there, which I thought was pretty cool. But there is still, to this day, no good reason why that is. So I'm just telling you, that's a law. It gives the relationship, but doesn't really explain. All right, so you can look it up on Wikipedia. I think I stole this graph from Wikipedia. I can't remember now. So this is what I do, and I do this a lot in the videos. I'll stop and say, hey, why don't you try to do this, right? So what I want you to do is try to classify these as observations, hypothesis, law, or theory. And I will just tell you, these examples are not that clear. Okay. On your test, if you're wondering what kind of things I'll ask about this, you might look at the test quizzes. They're not really for points. They're just so you can see what the questions might look like on your test. And I will use some of those questions on your tests. Okay, so those are posted in the modules down at the bottom for each exam. So I'm going to pause the video. You decide whether or not it's one of these things, O, H, L, or T, right? And then maybe why you think it's that. And then when you come back, I'll have what I think it is. And then I'll just tell you, these are hard to do. And I sometimes will go through this thing and change it as I'm saying it. It probably will happen. So let's see. We'll pause. And when you start, all the answers will be there. Okay, so here we go. Bad luck results from walking under a ladder. I think that's a hypothesis. Could be an observation. It's kind of hard to tell, right? But it's probably a hypothesis. And then it's testable. You can just walk underneath the ladder, and then you could gamble and see what happens, right? So it's a testable thing. Oil floats on water. That's most likely an observation. That sounds like something you see happening, right? Oil floats on water because it's less dense. Now that sounds like a theory because it's providing an explanation of why the oil floats. And wood burns. I mean, I hedged my bet. I said it's either an observation or it's a law. Law because it doesn't provide any explanation. And that's the hard part about observations and laws, right? Neither one of them provides explanations. So I don't know if they're saying wood burns, as in it burns, or actually they're saying wood burn, because that would make it an observation or a law. Now, if you look at the next set, right, when wood burns, oxygen is consumed. Now, I don't know if that's an observation or a theory. Theory being an explanation of oxygen being used in the combustion process, or if it's just an observation that they actually measured oxygen usage. It's an easy experiment to do, actually. Maybe I'll show you sometime on a video. And then heavier than air objects always fall towards the center of the Earth. Like, I don't know if that's an observation or a law. I don't know if they were saying that's the way it is. If that's the way its statement is, then it's a law. But if they're saying this is what we see happening, then it's an observation. I'm kind of leaning more towards the law on that one. And matter is composed of atoms. That's probably a hypothesis, because you can't see atoms, right? So hard to make that observation. So it's a hypothesis. And then crime rates increase when the moon is full. And yeah, so anyways, you might be crazy. Who knows? Some people say that's true. I don't know. I mean, the data kind of supports that weird things happen when the moon's full, but I think that the data might be flawed. I don't know. We'll go with it.